All right. Thank you. So now can everybody see here for the most part? Okay. Thank you. Okay, so thank you for the introduction. It's great to be here. I've never been to one of these before, but I'm excited to be at this one, obviously. Speaker's good. When Andrew got in touch with me in February, he asked me to give a talk on brewing because I was very tangentially involved in a group of students that won some brewing competitions associated with Case Western. But I had literally nothing to do with their accomplishments. And I don't actually know that much about brewing, but I do know about interfacial phenomena. I know a lot about beer. And how it applies to beer. So that's what this talk is mostly about. I'm also gonna mention wine and bourbon at the end, but most of it is beer. And what I've shown here are two of my favorite beers, and then Miller Lite, which I'm going to be talking about for this presentation. So before I really get started, there's some disclaimers. So I'm not actually an expert in beer, wine, or bourbon. I don't really brew professionally. I don't know a lot about wine or bourbon in making it, but I am what I would consider an aspiring expert in something called interfacial science. Okay, interfacial is the word I'm going to be using a lot this evening.
What does it mean?
Great question. Interfacial refers to any phenomena, or it refers to interfaces, which are the boundary between two portions of matter or space. So a great example for this talk of an interface is that of the thin film of liquid that resides between water, mostly water, and CO2 or nitrogen, which of course is relevant for most beers. Okay. So when I say interfacial or interface, I'm referring to the space in between these two phases or two materials. This could be relevant for, solid materials and liquid, to solid materials, to liquids, etc. This talk is about beer, wine, and bourbon, but as I hope you'll know or see or learn by the end of this talk, it really could be called shampoo, body lotion, and shaving cream, or house, car, and finger paint, because the underlying science that I'm talking about are applicable to a whole host of products that you use in your everyday life. And my goal is to show you this, that interfacial science is everywhere, and it is pretty cool. The other word that I want to explain in the title is flatland. Okay, so flatland in the title refers to this book. This is the cover of the book. It's called Flatland, A Romance of Many Dimensions by Edwin Abbott. And this book is basically like an abstraction of interfacial science and how that applies to a community of beings that live in this 2D world. So it's about people that are only 2D, we're 3D, but they're 2D. And it describes this two-dimensional world and explores the nature of dimensions. It's pretty interesting. If you like what you hear tonight, and you don't necessarily want to read about the science, but you kind of like the abstraction of like how to think about these things, this might be the book. And you can see here, the four kind of like things for comparison. Point land, there's no dimensions, just a point. Line land is single line, one dimension. 2 dimensions, flat land, that's us. And then 3 dimensions, that's space land, that's where we live in our everyday lives. Okay. So that's what flatland refers to in our talk this evening. Okay, so why does any of this matter? Why do interfaces matter? So if you think about taking two materials, so in the case of beer, maybe the beer that some of you are drinking, those two materials would be mostly water and CO2. In the case that of the beer that I'm drinking, that would be nitrogen and water. But if you take those two materials, in this case, substance A and substance B, you process them. I'm a chemical engineer, so we care a whole lot about processing. And you do it in such a way, it's cut off down here, but if you do it in such a way that one material is dispersed such that the length scale of the individual entities are between a nanometer and a micron, you create a ton of interfacial area. And just to give you an example, the human hair is about 100 microns in size. Okay, so this is you're taking these materials, so the bubbles in your beer are on the scale of, depending on the beer you're drinking, let's say 100 microns or less. Okay, and when you do that, you're creating a huge amount of interfacial area. This is applicable to basically every product that you use in your everyday life, with the exception of maybe tap water. Paints, mayo, milk, beer, blood, ice cream, soap, chocolate. These are all materials that are dominated by interfacial phenomena. They're called colloids. I'm not going to use the term colloid because that would just get me in more trouble, but they're dominated by interfacial phenomena. And just to give you an example, if you take your shaving cream at home and you spray about, I don't know, about a cup worth of shaving cream, you'll get a material that has an internal interfacial area of about 130 square feet. Okay, so maybe the area of this stage, or a little bit more, maybe. But that's just a cup, right? And there's tons of examples of this. You know, if you use carbon black or use other materials, where you have materials with huge amounts of interfacial area inside. And as a consequence, like I said, this makes it such that interfacial phenomena, the thing that I'm talking about, really dominates their behavior. Okay, so you use things every day. Again, why does this matter? I know we're kind of down the street from Sherwin-Williams. Lubrizol is not far away. But just, you know, a conservative estimate of a subset of three industries: coatings industry, consumer products industry, and beer industry. How much do you think globally the coatings market is?
The percentage of those three groups?
No, sorry, total money.
Oh. Gazillions?
Not that high, so about 200 billion. So the global coatings market is about 200 billion. Consumer products, about 670 billion. Yeah. And beer, I would think lower. Everybody guessed lower. We drink a lot. It's $757 billion just beer. These three, I mean, now, so they have portfolios with other beverages, right? AB InBev, which has a whole host of beverages. Heineken, Asahi, Japanese company. But in any case, you know, you get the scale. Just these three industries are over $1 trillion in market share. And each of these companies, you know, Sherwin-Williams, I think, is a great example. This is what I use with students, is that, you know, Sherwin-Williams is a $16-17 billion company. You know, they spend hundreds of millions of dollars on research. That is the research enterprise of CaseBuster, right? So Sherwin-Williams, just interested in paint, spends as much as research on the whole of one of the top research universities on the planet. Okay, so now let's get to the fun stuff. Hopefully by now you are guessing, or I hopefully have proved to you that this is important. So let's do the fun thing that's kind of silly. Okay, so this is a beer. It's a nice beer from Urban Artifact. It's a brewery in Cincinnati. You can see that it is dark red, purpley pink color. Has a nice kind of purplish foam head. This thing at the top, the material that's above the liquid is a foam. Okay, foam referring back to kind of the slide that I showed earlier, is consists of finely divided bubbles of gas dispersed in a liquid. So you're dispersing CO2 in this case, CO2 in water. Okay, and that's a foam. And it remains stable. So, but when you drink water, for example, you don't get this type of head. So why is beer different from water? Beer is different from water because beer has stuff in it that makes foam stable, what's called stable. So if you zoom in further, so this is a photo of a foam taken with a microscope. And if you zoom in even farther, you can see there's this gas bubble here, there's another gas bubble here, and you have this liquid in between. And the thing that's happening at these the planes where the gas meets the liquid, the interface, is what causes stability in these materials. This is flatland, right? So this is why interfacial phenomena in the case of foams matter so much, because you have all of this interfacial area where stuff needs to happen in order to make things stable. So then why would something be stable? What do you do to make something stable? It turns out that you can use microscopic materials, so it's very, very small materials located at this interface, at this boundary, in order to stabilize these foams, to make sure that you have a nice foam. And the thing that you add is something called a surfactant. Hopefully this is the most jargony thing that I mentioned, but it's called a surfactant. Surfactant stands for surface active agent. And a surface active agent or a surfactant consists of, it's basically a material, it can be a molecule, it can be a particle, that has some parts that like one phase, like the CO2, and some parts that like the water. So as a consequence, it sits at the interface, right? If you're between two groups of people having the conversation, and you kind of like this conversation, you kind of like this conversation, you might stand in between them. And that's what a surfactant does. It stands in between, it sits at the interface. And there's all types of reasons why that then leads to stability, which I won't get into, but those are the things that are necessary in order to make things stable. And it turns out that beer has a ton of stuff in it that can make things stable. You can't see down here, but acids, proteins, ions, carbs can all stabilize foam. Okay.
Yeah.
Yes. Especially in the morning, right? Yeah. You need a good breakfast, yeah. So, okay, so this is a beer head, right? So this is, I'm going to talk a little bit about experiments. Okay, so this is Miller Lite. This is a video of a head of a beer that is formed when you pour it. So the head of a beer forms when you open a can, the CO2 comes to equilibrium, CO2 bubbles start to form, you pour it in your glass, and it forms a head, and then it rapidly decays. Okay. So Miller Lite has a rather totally fine head on it, right? But not in particular special at all, right? But it turns out that there are beers that have heads that are quite important, right? So foam character, and this has been shown in research, foam character, the head of a beer really actually matters quite a bit to consumer preferences, right? So you order a Guinness in part because you like the head. You might order this fine Belgian beer because you like the head on top of the beer. So because the head of a beer is important to you, it's important to the company selling it, right? So as a consequence, foam character can be measured and it can be engineered, it can be tuned, just like any recipe, right? If you get a Guinness in Cleveland versus California versus Ireland, sure, there are people that will say it tastes a little bit different, but for the most part, you're going to get a beer that has a head that has this almost identical character regardless of where you sit. Just like if you buy an iPhone in Cleveland, California, or Ireland, you're gonna get an iPhone that should be the same, right? So you can measure this, okay? So what I'm showing here is just a simple way of measuring this phenomenon and then interpreting that phenomena based on the formulation of the beer. We can use image processing. We do a lot of image processing and stuff in our lab, but in any case, you can measure this head and then you can fit it with a very simple exponential decay that basically collapses all of the complex stuff that is happening. So don't worry about the details, but the thing that you should worry about is the rate constant. So you can fit it such that you get a rate. Oh, okay, thank you. Rate constant is the jargon or exponential is the jargon? That's fair. I can, okay, so HT is the height of the foam as a function of time. So if I were to measure this, the height of the foam in many points in time, I would get H of T. That's fair. H naught, H0 is the initial height of the foam. K is the rate constant. It's how fast the foam is decaying, right? So a large number means it's decaying fast. A small number means it's decaying more slowly. And you can measure these things and you can get a measurable difference between Miller Lite and Orval, right? So Orval, which is a very wonderful Belgian beer, has a very small rate constant compared to Miller Lite. Okay. You can also do this for Guinness. Guinness is maybe the most famous with respect to head formation. Guinness is interesting because it actually forms a head that increases in thickness, in height, on the time scale that you do the measurement, right? So all beers form head. So they increase from 0 to some number, but Guinness happens substantially longer than like Miller Lite, for example. So you can actually measure this. So it increases in height and that's extremely stable. It stays around forever. The head on my Guinness, which was poured maybe an hour ago, it is still there. It's still there, right? So it's very, very stable. If you then do the analysis that I've shown for rate constant, that can be measured, right? So you have the Miller Lite again, you have the Orval, but then you have Guinness way down here. It almost can't be measured how small the rate constant is. Okay. So then the question becomes, so this would be an example of an experiment done in the research center for these breweries. So then why is this? It's because of the differences in formulation. It's the differences in the recipe, mostly. Miller Lite has very few proteins and carbs. It's filtered for clarity, so there's not much to stabilize the interface. You just don't have a whole lot there. Orval has more protein and carbs than Miller, but it is also bottled condition, meaning that if you drank the Orval before, there's a layer of sediment at the bottom, which can also contribute to stability. And you can actually, observe this if you pour out that sediment. And even what has happened in the US, this is not done in Belgium. I worked there for 2 years, so I would know, at least 10 years ago, they didn't do this. Now they do this in the US market where they actually pour the Orval such that you won't, because US consumers don't like sediment. They pour the Orval in a glass such that you get a clear beer, and then they give you a tiny little beer on the side that has all the sediment. And you can even see in this photo, the beer with the sediment has like this very thick head that is very stable. Okay, and that's likely because of the presence of sediment. Okay, so you're already getting kind of interesting interfacial science here. What's happening with Guinness? Guinness is like a whole, you could do a PhD on a kind of Guinness. You're laughing, I'm actually serious, you could. So there's probably more than two, but there's at least two interesting things about Guinness. One is that you get this growth in foam height, which is basically a consequence of, well, there's likely more reasons, but one of the reasons is because of this interesting fluid mechanics problem that happens where you get rising bubbles that create a clear layer of liquid along the edges, which then entrain some bubbles, and as a consequence, you get bubbles that appear to be going down in these waves. This is called the boycott effect, which could be another good science cafe, but in any case, is an interesting fluid mechanics problem. The other reason, and this is really the okay, boycott is a guy's name. I don't know what boycott. I'm not talking about it. Next science cafe. So, the more important thing here, though, is that Guinness is pumped, or it's poured with nitrogen instead of CO2. Nitrogen produces typically smaller bubbles that are less soluble in the liquid, and as a consequence, that's one of the big reasons why you get this very stable nitrogen. You get this very stable gas. Okay, so how is foam destabilized? So I went to a proper state university where I learned about this. How do you destabilize beer foam? So I would do the thing, and I'm sure a lot of you did, where you rub your nose a little bit and you put your finger maybe in the beer head to destabilize it. Your nose has a lot of fats and waxes and things along the edges. And you would kind of anecdotally kind of find that maybe that helped with the foam a little bit. This actually makes sense because in order to destabilize a foam, in order to go from a foam that's very stable to one that's not, which actually is quite relevant for a whole host of industrial applications, but you need to break up this lamella. You need to break this little thin liquid of film, which refers to a lamella, by introducing particles that don't like the presence of the lamella. They don't like to be in this little film. So if you have a wetted particle, a particle that likes to be in the film, that would stabilize your foam. If you introduce a particle that's non-wetted in this little film, then that will help to destabilize the foam. So this makes sense because in the beer scenario, this liquid film is water basically, and the little particles that you're rubbing from your nose are like oil, basically non-polar little particles, and that will tend to destabilize the foam. Okay, so that makes actually total sense. I haven't done any measurements on this, but anecdotally that all makes sense. Okay, so the last thing I want to say about foam, and then finish up here, is there's lots of other cool examples. I've shown you 3, Miller Lite, Orval, Guinness, which are kind of distinct and interesting, but there's lots of other examples. Pilsner or Kel, which is a tank beer from Prague, you can get it in cans, but if you get it in Prague, you can get them to pour you 3 different versions of this beer that systematically alter the amount of foam that you get. There's also a couple of really classic German beers that have this long developing head that self-filter. Coors makes one, but you can basically only get this in Golden, Colorado, which is where Coors was brewed. And just so I'm true to my title, I just want to talk very quickly about wine tiers in bourbon. So some of you might have observed this evening. I don't know if anybody's drinking wine. The effect of wine tiers. This actually was first observed by J.J. Thomson, like the J.J. Thomson that you learn about in undergrad physics or chemistry in 1855. He has a very long-winded explanation here that I won't, or at least description of the observation. I don't know if he totally understood what was happening at the time, but in any case, we know now. So if you look more closely at this wine glass, you can figure out what happens. So this is just a diagram of your wine glass. You have some alcohol and water. If you swirl it, then you form a meniscus. You form a thin film of wine. You didn't know jargon, right? That for a variety of reasons will cause alcohol to evaporate very quickly. And once you cause that to happen, then you actually change what's called the interfacial tension, which is the force that an interface feels as a consequence of the chemicals that are at the interface, that then causes fluid actually to pump up the rim of the glass or up the side of the glass such that you actually get a little drip here, which then will fall down. And it's this action of evaporation, a change in what's called interfacial tension, which I know is probably jargon, but is change in interfacial tension. You get a gradient, which causes fluid to pump, you get a drop, that drops down. So that's, okay, good. Okay, and the last thing I want to talk about, because I know I'm over, but because this is really cool. And again, this has lots of really important applications, but bourbon. So there's lots of stuff in bourbon. I mean, it's and by stuff, I mean like particles and surfactant-like materials. If you dry a drop of bourbon, so these are all dry drops of bourbon. If you just take a little bit of your bourbon, put it on a glass slide, you put it on a whatever boundary, you dry it, you'll get these really interesting patterns, and the patterns are actually consistent with the type of bourbon that you've chosen. It's consistent with, you know, if you have different ages of the same bourbon, or if you have different bourbons entirely. This changes, and actually this faculty member here, Stuart Williams, good friend and colleague, who's in mechanical engineering at Louisville, he kind of discovered this. There's other people that hinted at it, but he really discovered this. He has a website called Whiskey Webs where he sells like these images, these really beautiful images of these webs. So why does this happen? It's actually very similar to the wine tears phenomenon, where you have this drop of liquid that has all of this dispersed stuff in it. And as a consequence of evaporation, you get gradients, you get changes in concentration of the stuff along the surfaces, which drive flows and then create patterns. And then this is actually very relevant to coffee as well. So there's a phenomenon called the coffee ring effect. You likely have observed this, where if you dry a drop of coffee, you'll get a thick ridge of accumulation of material around the edges, and that's because of similar flows. Okay, and you might say, well, so this is bourbon and coffee, but you know, if you're making printers where you're literally putting down little drops of suspension, you know, every fraction of a second, and you need it to look uniform, that's actually very relevant. Okay, so this is really important to those applications too. So okay, so hopefully you've learned that interfaces are everywhere, right? The boundary between two materials are pretty relevant and everywhere, and that even these simple product features like the head on a beer, but also the way your shampoo works, the way your little like detergent pods work, are engineered through the formulation of that product. And there's lots of people like me that spends lots of time figuring that out to make it work for you. Okay. So with that, I just want to thank the organizers for inviting me. Hopefully this fit what they were looking for. I thank my group too that, you know, let me, or some of them are here, do like the stuff on real things so I can mess around with beer. And then of course we collect preliminary data occasionally. And then I think there's lots of, I'm lucky to have lots of sponsors of our research, but this in particular fits in with a grant from the National Science Foundation. So thank you, and I'm happy to explain as much jargon as you'd like. Okay.